Hello, everyone.
Dara.
We are now starting our roundtable discussion on the topic of casting versus metal 3D printing, considerations, economics, and technical insights. Led by Dan Brunermer, technical fellow at ExOne. We also have on our panel Dave Rittmeyer, customer core and AM manager at Hoosier Pattern, Mike McLean, GM at 3D Printed Parts, Thomas Becker, president of ACTech North America, and finally, Frank Medina, Director of Technology and Engagement at UTEP. All right. And so I will let you get started.
Well, I see everybody but Dave. And I know I saw Dave in the audience here somewhere. So, Janet, I see you're kind of still in this. If you could pull Dave up, that would be great. Okay, so while that's getting worked out, I'm just going to get started here. First, I'm going to go around my panel and ask them to introduce themselves a little bit, talk a little bit about what they're doing at their companies. We're going to focus today on, the differences and the similarities between direct metal printing of parts, whether that's laser or whatever, and indirect printing of parts through various types of castings, die casting, sand casting, etc. So Mike, I'm going to start with you. If you would just tell us a little bit about yourself and what you do there at 3D Printed Parts.
Yeah, so I'm the general manager of 3dprintedparts.com. We're based in Grand Rapids, Michigan. We provide laser powder bed fusion and high resolution plastic printing to the aerospace, automotive, and consumer products markets. So our intent is to be a contract manufacturer for these industries going forward as additive continues to scale.
Tom?
Hello, I'm Thomas Becker. I'm running the North American sales office for ACTech. ACTech, we are a provider for rapid prototyping of sand investment casting, including machining. Our goal is to provide prototypes in a close to production method as possible, in the shortest lead time possible. And I'm working in the industry for over 20 years now. Still, it's very amazing how dynamic our industry is. And I'm also amazed on the impact actually our industry had on product development and design.
Yeah. Frank, why don't you tell us a little bit about what you do down there at the Keck Center at UTEP?
Yes, of course. Thanks, Dan. So I'm Frank Medina. I've been in the industry for over 20 years too. We started, I was one of the co-founders. I was working with Dr. Wicker since early 2000. Since pretty much 2000, I'm developing the WM Keck Center for 3D innovation at the University of Texas, El Paso. We started off with plastics, and in 2007, we purchased an EBM system. We currently have over 50 AM machines, right? We have 3 EBM systems. We have SLM, Econity, EOS M290, and other laser processing systems. And then also we have a wide variety of FDM, binder jetting. Of course, we have 5 binder jetting systems, now. So we do a lot of research in that. Also, a little bit more about myself. So I graduated with my PhD in 2013, and then decided to go into industry. So I went to Arcam. Worked with Oak Ridge, for about 3 years, developing their relationships there with additive manufacturing and metals, and taking some parts into production with EBM technology, and also those processes. And then from there, I went to EWI, and I was a technology leader in additive manufacturing, and also the director of the Additive Manufacturing Consortium, which I'm still a consulting director, and helping grow additive manufacturing with different companies. So what we've been doing lately in additive manufacturing here at the Keck Center is we've been helping companies go look at additive manufacturing and then trying to go into production with different technologies. So I have a wide variety of systems that we have access to and knowledge. So that's one of the reasons I'm here to help you guys understand.
Yeah, great. And, I got to say, I still don't see Dave Rittmeyer on my screen. Dave, are you here?
He's having some technical difficulties. He should be on in just a few moments.
Okay, great. So we'll circle back around. Oh, we'll circle back around to Dave when he's on. So, okay, let's talk first, guys, a little bit about the technical capabilities of, direct metal printing versus some of these indirect methods, whether it's die casting or sand casting. Tom, why don't you lead off and tell us a little bit about what your experience at ACTech has been with the practical limits of what you see in metal printing and in your investment casting.
Okay. For nearly 2 years now, when Materialise is by ACTech, we also have access to the 3D printing of metal parts. So we offer both to our customers, metal castings, sand casting, investment castings, and the 3D printing of parts. And what we are seeing is that our customers tend to stick to the procedure that is their production procedure. So if the production procedure is in sand casting, the best thing you can do is do the prototype in sand casting. So the benefit 3D printing of metal parts is bringing to this field is rather limited. On the other hand, we see if a part is really designed for 3D printing of metal parts, then it's of course an awesome technology that allows a freedom of design that is unmatched by any other process. So you occasionally, it's difficult to talk about projects because projects are often under disclosure and under confidentiality. Something what made the rounds a lot is like aerospace parts where highly complex assemblies were used, redesigned with 3D printing in mind, and now instead of hundreds of pieces, these things come together with just 2 or 3 pieces. And even despite the fact that 3D printing of metal is still very expensive, makes this unit cheaper and makes this unit better. On the other hand, sand casting, 3D printing of sand molds is around since the mid-90s. ACTech was founded on this idea. And what the 3D printing of sand is doing, it gives our customers and our engineers a tool at hand to go for ideas that were previously unthinkable. You can just shoot for casting or for changing a certain feature, be it that what we have seen in the past that I can talk about is if you go for turbochargers, for steel turbine housings, they used to have wall thicknesses of 5-6 millimeters 15-20 years ago, cut down step by step to 3.5, sometimes 3 millimeter wall thickness, but clearly as an effect that you did not need to make a tool to make the turbochargers, but we are really focused, the OEMs for this product focused on step by step using this prototype method, seeing if it's possible. In the end, it's a sand casting, and it was proved that the physical limit of this is lower than what was believed so far.
Mm-hmm. Mike, would you care to share with us a little bit about your experiences there, and maybe tell us a little, if I remember right from when we talked earlier, you guys are using direct metal printing to actually make die casting tools. Is that correct? Is that what I have in my notes?
Correct.
Would you tell us a little bit about that process, what its limits are, how you're actually doing it?
Yeah, so specifically what we discussed was high pressure and how laser powder bed fusion can support that process. So for anybody who's not familiar with high pressure die casting, this is generally used for larger components, things such as transmission cases, brake drums. Essentially, a tool is made that could be the size of a Volkswagen microbus, and 70 pounds of molten aluminum is injected in this tool with a fill rate of maybe 90 milliseconds. So it's really a controlled explosion. And within that tool set, there are very fine details. Like if you picture a transmission case and all the little ribs and features that go along with that, there's a corresponding tool. With some tools, you have an exceptional amount of wear when you get into those fine details. Mm-hmm. And with conventional machining, you're somewhat limited on regulating the causes of that wear, primarily temperature. So what we've been working on is creating conformal cooling channels for specific details within those tools. So for instance, a conventional tool detail may last for 10,000 shots. And say a detail for a transmission case. Through 3D printing of maraging steel and including conformal cooling channels, in some instances we can extend that to 50,000 cycles before a tool has to be rebuilt. So we're viewing, 3D printing and additive manufacturing kind of along that classic adoption curve of, a prototyping medium, a rapid tooling medium, and ultimately an end-use part production process. But we're seeing a lot of growth in the tooling and are beginning to see more and more within the end-use part. Thomas had brought up the part consolidation benefits of additive manufacturing that are being seen in that classic showcase of the fuel nozzle, I think is what maybe he was referring to. But while additive is viewed as an expensive process, if you start to account for the soft costs associated with all of the hundreds of parts that could be consolidated into 2 or 3, it really becomes cost competitive because you don't have all of the paperwork burden associated with qualifying hundreds of parts that could be consolidated. I think that's quite often overlooked.
Well, and I think that kind of interweaves pretty nicely with Thomas's comments about that if we're not designing for additive, we're not going to get the benefits of additive, right?
Yeah, that's correct.
Yeah. So Frank, you do you get into any? I know I've been to your place several times, as you know, and I've seen all of your equipment. Do you guys get into the castings at all? I don't seem to remember seeing that down there, but I really don't know.
So UTEP originally was a school of mines, so it's still a very hardcore metallurgy school. I think God, we're one of the few that are still around. So we do have a casting foundry in metallurgy. So we have been working with ExOne, to give that experience to students. We get Dr. Robertson is the one that leads this, and what we do have a casting facility and also a casting club. So we do work with ExOne, and they actually send us some tools, some sand molds, that we can actually inject. And a lot of the students are really liking this. It's been growing. There's a lot of this excitement on this. And then also something that they've been doing for the past couple of years is they've been doing different, for senior banquet, different awards, that they actually print them and cast them using regular sand casting.
Huh. Well,
so we are teaching them still. So
yeah,
good.
great. Okay. I'm glad to hear that we're supplying you with some molding forms.
That is, by the way, that's very interesting.
Yeah.
ACTech, we are located in Freiburg in Germany, and basically a lot of our roots is in a school of mines in Freiburg. It's one of the leading schools in Germany. So it seems something with castings and prototypes in schools of mines that has something to do with each other.
Yeah, I guess so. Well, I really wish Dave were here. Okay, so what I'd like to transition here for our last 15 minutes or so, and now this may be a little bit sensitive for you guys. I don't know how this is going to go, but I'd really like to talk to the audience about the economics of these choices. Like get down into some hard numbers. I know that I can't speak for Dave. I do know what the costs are. In terms, I know what we quote, in terms of per cubic inch of sand printed or whatever, but I'm not so familiar with the actual cost of pouring the aluminum. But so, okay, Mike and Tom, I will start off with you two again. Tell us a little bit, if you can, Mike, about total costs of making a high pressure die cast component. Like, how do you approach it with your customers in terms of, I don't know if you charge by the pound or kilo or by the surface area times Z. We all seem to have our own complicated models for the generation of the actual 3D printed part. But can you talk a little bit about the total cost of getting from your 3D print to your final die cast part?
Yeah, it's pretty simple, really. It's time and material. So we have a standard rate for the machines that we use, and we just, we'll take a quick volume assessment of a part and apply our time estimate. And it's really straightforward.
Yeah, okay. You have a pricing model. It's well developed. You feel pretty confident in it that you can take a geometry, put it in there, and come out with a good cost for a customer. Do you have any kind of shorthand of expressing that cost? Or is it too complex? I mean, I know it's simple,
relatively
but
complex.
It's not.
I mean, so with a Diecast tool or injection mold tool for that matter, it's pretty straightforward because those tools generally have drafts and they're not going to require a bunch of additional supports or engineering time to figure out how to build it. So those are relatively straightforward, and it's really just a time and material model where we multiply the time by a factor and arrive at our cost with surgical tools or consumer products or things that aren't necessarily easy to get to additively or otherwise, then we have to account for more engineering time or support removal time. With the Diecast tools, we don't even necessarily consider post-machining because those tools don't require like an A surface finish, and oftentimes you can get to ready to use level from printing, heat treating, wire EDM to remove it from a build plate, and then sandblasting, and you're ready to go.
Tom?
Costs, it's a bit a difficult subject, how you value costs, because it's also, sometimes you are not exactly buying what you think you're buying. If you compare us with a regular foundry, we are just amazingly expensive compared to the I mean, it's just what it is. Even if you go to a prototyping foundry, we are often multiply the price of a other foundry. The point is here, we are not selling so much a casting. Yes, casting is the piece of hardware you hold in hand afterwards, but what we are actually selling our clients is time. And if you can have, just imagine a development process in a big OEM, they have a new idea, there's a new machine that needs to be done, it has castings in it. Getting this casting in 8 weeks, what might be state of the art, then this casting has a certain value. If you can supply this casting in 4 weeks instead of 8 weeks for the engineers, and it's just strictly focused on prototyping. If you can supply this in 4 weeks, you have this time difference of 4 weeks, and those 4 weeks actually have a value because you're earlier to the market with the product, you're the front runner in the market, you can sell longer. So this maybe makes worth investment. And so this comes now down to why is our cost so much more expensive? Yes, we have an hourly rate for our ExOne machines. Yes, we have an hourly rate for our CNC machines in our CNC shop. Yes, we have a rate for what a pound of iron or steel or whatever costs, or name it. But underlying under the whole economy is our first goal when we plan a project is time. The second goal is time. The third goal is time. And then in far distance comes maybe costs. If we can make something a day long faster and it costs a couple hundred or a couple $1,000, then we are just doing it because our clients require it from us.
Right.
So really cost, yes, we look after costs, of course. I mean, we are not having an endless stream of money, but cost is really a secondary goal when going to ACTech. You're really going for fast and for being quickly in the time. And then it's up to our customers to decide, is the extra weeks they are saving with us or the 2 weeks they are saving with us, is it worth their money, or are they maybe better off going to a good quality foundry that can use ExOne's expertise too? I mean, you can buy the molds from ExOne and you can pour it, and other foundries, they know how to do their stuff too and do it in good quality too, but they may not have the streamlined process in place to do it in the 4 weeks like in my sample, but they may need 6 or 7 weeks and can do it like at half of the price.
Yeah. Hey, Frank, I know that you're really interested in the economics discussion and debate here. Why don't you tell us a little bit about how this affects you? I know that you do work a lot with like you had said, you work a lot with businesses, you're not just down there doing R&D, you're trying to enable companies to take advantage of this additive manufacturing. How do the costs and economics affect a group like the Keck Center?
No, so for example, the way that we work, right, our main goal is to produce students, right, produce kids. But what we're really focused on is trying to produce, the next generation workforce for additive manufacturing, and that's something that's very needed, right? And what we're doing this is we're helping them with real life challenges, real life projects. We work a lot with the Army, we work a lot with the Air Force, we work with a lot of industry, not just the local industry, but international. And what we always try and do when they come to us and ask us, how is additive manufacturing really going to benefit us? If you have a part that you've been casting for 20, 30 years, it's not really going to help that much if you go into metals additive, right? What we tell them is if you're going to compare laser or electron beam to casting, they're always going to lose, right? Price-wise. So you have to take advantage of the new stuff that's coming out, like design for additive manufacturing, like you guys hit it right in the nail, right? To combine parts, make it lighter, make it more complex, and that's kind of what we teach our kids, how to start designing for additive. Especially when you guys are going to produce. I also tell them a lot, and show them different types of models, right? Additive manufacturing makes sense to a point, right? If you're going to go into mass production, there's not enough parts or machines in the world that will be able to produce these many parts, right? Or you're gonna have to do a GE and start making your own machines and buying them, right? Which is kind of
cheaper to buy the company.
Yeah.
Well, and I think that was kind of highlighted by the EOS presentation. That was the first time I've seen that exact graph of the whole life cycle of the part and where additive fits in that whole chain. And I think that reinforces what you were saying there.
Stuff, I think that's perfect. But like it's a numbers game pretty much,
So I got a question from the group here that seems pretty popular. So this is from Todd Spurgeon. Thanks for the question, Todd. Considering requirements for primary and secondary machining, and this is for the group, what lessons from casting processes are most directly applicable to design for additive manufacturing for laser-based powder bed fusion of metals? So what lessons can we take from casting to apply to our laser bed parts from a primary, secondary machine?
I think the big takeaway that I've seen is that they are both near net shape production processes. Saying casting versus powder bed fusion it's relatively generic comparison. I would never compare powder bed fusion to the sand casting process.
Yeah, sure.
I would say it's more comparable to die casting or investment casting, although there are metal additive processes that would be comparable to the sand casting processes. But with additive, we're not limited to clearances that you need to extract tools or slides or inserts, and I think that's a good takeaway. Is that, as Frank alluded to, there is more design freedom, but there are still additive constraints.
Thomas, you look like you have something you want to say.
As Mike said, it's hard to compare. The only thing you can take from it is a net shape solution. Both of them are net shape solutions. Both of them have tolerances. I guess the sand casting has a bit more tolerance than a 3D printed metal part. Nevertheless, the 3D metal part has still tolerances. So you have to be aware of that certain shapes you cannot print. Just think about the thread, right? You can print a thread, I'm pretty sure about that. But if you want to have a really good thread, then you have to machine it afterwards. So in this sense, you have to add machining stock for a 3D printed part and machine it. And in principle, it's the same as for sand castings. The only difference is in the sand casting where you maybe add like 3 or 4 millimeter machining stock, your printing guys add only a 0.5 millimeter. But that's pretty much it. I really would not compare it.
Okay. So is another question I got here that seems kind of interesting to me. This is from Duncan Gibbons. Thank you, Duncan. Hi all, there is often mention of potentially applying casting factors to metal AM. Is this recommended, and will the current casting factors have to be revised if to be used for AM?
Is it safety factors?
Well, I'm
or-
not
Yeah,
entirely sure. It's for aerospace.
Scaling.
Oh, okay.
Maybe we don't have an answer for that one. Okay, this is another one from Duncan. What kind of, oh no, it's not. This is from Priyesh. What kind of post-processing activities, Mike, do you need to do? I mean, I know lasers near net shape. How much machining post-production goes into actually making the casting tool, the die casting tool?
So, the generic post-processing arrangement would be printing, depowdering, heat treatment, generally wire EDM of the tool off of the plate. And from there, it depends on the portion of the tool that the insert has to fit into. We would generally have the netting features, like the features that are going to pocket within the existing tool machined. But the actual surface features, the intelligent geometries, I would call them, we rarely touch these days.
Okay. Hey, Duncan, thank you for the follow-up. Yeah, he was asking about casting safety factors, that the FAA made mention of potentially using them in the future. But I see Dave Rittmeyer's outline on my screen. Dave, can you hear me?
I can hear you. Hopefully you can hear me.
Okay, I can hear you just fine. We're down to our last 3 minutes, so I want to thank Link 3D and the group for coming together here. But Dave, I'm going to go ahead and give you like these last 2 to 3 minutes. I'd like you to talk a little bit about what you're doing there at Hoosier, how this all fits in. I hope you've been able to at least hear the discussion to this point, and you get the last couple minutes, so go.
I appreciate it. Yeah, I was able to hear some of it. Unfortunately, doing a whole bunch of typing back and forth, trying to get, apparently the system let me in. Well, we have 4 of the ExOne S-Max printers here. We are running around the clock, 5 to 7 days a week. We have probably about 150 production jobs for sand castings. We do a lot of molds for prototypes, but like I said, we have about 150 jobs that are production. That might be 50 a year. It could be, we have one right now, we run 6,600 pieces a year. It's about finding the right fit, applying the tool where it makes the most sense, and that's what we do.
And you do more than just sand casting. You also have plastic machines there. Could you tell us a little bit about how you use those?
Yeah, we have, actually our second one's coming. We have 2 FFF or FDM machines. We'll use them, we'll print prototype patterns. We'll print just, touch and feel parts for customers. We use them for jigs or fixtures. Honestly, we're printing a lot of tools for the sand printing side with those to reach in hard to reach areas, make special customized tools.
Huh.
Applying it all over the shop.
Has digital production of castings opened up any new capabilities as far as in casting itself? I mean, can you are there advantages with the digital molds? Can you do a thinner wall? Can you do
Absolutely. We have one in particular where the capability, the CPK numbers went from a 0.8 to a 2.6 the second they went to printed cores. So they're able to get thinner walls, more consistent castings. So now they can design for that and get, say, water jackets closer to a fire deck face, or just other options.
Mm-hmm. Well, great. Well, hey, listen, I see that I am at the end of my limit, and my clock says 11:30, and I have a stopwatch that's at minute 29. So I'm going to start wrapping this up. First, I want to thank Link 3D for hosting this event and inviting us all to participate. Dave, thank you so much. I'm sorry that Sorry that you only got here for the last 3 minutes. Frank, Mike, Tom, it was really great having you on the panel today. Thank you for sharing your insight and wisdom with the rest of the group. And again, I can't say enough nice, great things about Link 3D and how quickly you were able to pull all this together. This is a wonderful conference, so thank you very much.
Thank you.
Thank you.
Thank you.
See you live next year.
We'll see you next year.
Thank you to everyone.
Bye.
We will now, in just a moment, we'll begin our next presentation. So I will go ahead and start this one and start the next one. Thank you, everyone.
Thank you.
Yeah.